Hello, this video is entitled Change of Variables by using something called Jacobians. And we'll sort of set up what that is, and then you'll see here shortly why this change of variables can be useful for double integrals. Now let's start with a single integral that we're familiar with here, the a to b f of x dx. Now suppose that x equals g of u, and therefore dx would be g prime of u du. In other words, g prime of u is just du dx, but the dx is here, and it would then look like this. And then we would let a be g of c, and b would be g of d. All right. Now when we come down here, so you see it's putting a g prime of u into the integrand. Now in double integrals, it's kind of the same idea, except it's going to produce several little products here, partial derivative notation, because g would have a partial respect to u and v, and so would h. And we have this term called a Jacobian. And that is absolute values wrapped around that Jacobian. And this is going to be something we have to calculate when making the change of the variables. So the Jacobian, if you're familiar with a little bit of linear algebra and something called the determinant, that's what it is. I mean, even if you don't know what determinants is, just use what they are. Just use this rule right here. So it's the partial of x respect to u times the partial of y respect to me, v, minus partial y respect to u times partial x with x respect to v. Now this is these bars, look like absolute value. That's what's called determinant notation. But what kind of makes this a little bit confusing, and hopefully you'll see when I do the examples, that though when you use it right here in this formula, those are absolute values. So the determinant symbols down here is producing this result, which goes up here, but then you take the absolute value of that result. So it's a little confusing that the determinant notation looks the same as absolute value. All right. So here we're going to change the variables, and this is where this is going to be important, and why you'll see this is useful when we start doing integrals. We're going to transform that region of integration to become a rectangle. And rectangles are always delightful to integrate because that means the inside limits of integration are constants, just like the outside are always constants. So it makes it real easy. So no matter if you did the integral with this region of integration, if you did this in terms of x or y, you're going to have to break this up into several pieces. It would be several double integrals added together. Like if you went this way, you'd have this right here, lower to upper, dy dx, lower to upper, you'd have three of them. And if you went left to right for dx dy, let's see if we would have two or three. We would have, I'll just use a different color, it doesn't matter, but I guess I could have left the other ones there. But left to right would be, there's one zone, here's another zone left to right, and another left to right. So it would actually be three double integrals in either order. This method allows us to transform it to u and v and solve it with just one region double integral and a rectangular region. So we have to get, let's see, x and y in terms of u and v. If they aren't already, you can actually sort of solve for them. And it really doesn't matter that much which one's u or which one's v here. So in this particular case, when you see you have a matching set here, like x minus 2y, and then an x plus y and an x plus y, I guess I chose that one to be u because that's what they did. Yeah, it wouldn't have mattered, but I was trying to make it match what was going on down here. So here we're saying for sure that u will equal x plus y. So that means u is going from 1 to 4 right here. And then x minus 2y will be v, and it's going from 0 to negative 4. And then I'm not sure if it showed the solution, or I've got one coming up. Usually I just give it to you x in terms of u and v to make it easier. But you would do the algebra here basically. You would let u equal x plus y, v equals x minus 2y. It's not that bad, but you would just kind of substitute around till you got x in terms of u and v. Like, let's say if I took those two equations, and you can see they both share an x, and let's say I make the one over here, I'll take the negative of it. I'm using addition by elimination. So if I took the negative of this, that would give me an x and a negative x. So if I take the negative of this and I add those two equations together, because now the v would be negative, I would have u minus v, the x's are gone, and then I'd have y plus 2y, which is 3y. So if 3y equals u minus v, that means y would equal 1/3 u minus v right here. So that's all they did. They just took the algebra and eliminated. So you could do the same thing for this one. If you multiplied this one by 2 to eliminate the y's, and then it would work the same kind of way, and you would end up with this. So that's all that's going on there. Now, once we have that established, then they're coming up, they're showing you what the xy coordinates are here, but that's not really necessary. All we need is the limits of integration for the u and v. So we've transformed this region up here. They're just identifying what those 4 points were on the graph, but we don't need those. And then now it becomes a different coordinate system with u and v, and there it is, a rectangle, as promised. Now let's see if we can put this to use now in a double integral. Maybe the goal here, what they were doing, is just this might be a verification process to make sure that these equations are correct. I'm not saying you're going to have to do that, but they're making sure they're correct by putting in these u's and v's and making sure they produce those original points. So that's more of a checking process, not necessary. So here's another one. It's just asking us to set it up real similar to that last one. And so it's giving us the 4 points in rectangular form. So you take the two equations, and I got rid of this time I'm just getting u in terms of x and y, and then v in terms of x and y to come up with the coordinates. So you add those together, that we know the v's would cancel, and you would have u equals x plus y. And here I multiplied by 2 to get the u's to cancel. And I end up with x minus y equals v. And then I'm now plugging in the points on this rectangle, the tilted rectangle, to give us our new coordinates in terms of u and v. And this is going to happen every time. You're going to see two numbers are going to be the same, and then two other numbers are going to be the same. And then we have to coordinate with what the v's are. Because the u's being the same, that means we know u is going, if there's a 1 and a 3 and a 1 and a 3, u will go from 1 to 3. And then we have a negative 1. It doesn't matter the order, but we have two negative 1s and we have a 0. So that means the limits of integration then would be negative 1 to 0. Always, smaller number first. I generally don't ask you to do this to where you construct this graph, but that's what it would look like with those new points termed plotted in terms of u and v on a rectangle in a UV coordinate system. All right, so let's put this to use in an actual integral like we're going to do right here. Where we actually, we take the Jacobian. So this one has x in terms of u and v already, and it has y in terms of u and v. So we're good to go here. It's like that first example I showed you. If u and v were in terms of x and y, back up here, you would have to manipulate it to make it, you would have to manipulate it to get it in terms of x and y in terms of u and v. But here we already have that, and we did for the last problem too. So, for the Jacobian, we're already set to go, but I'm doing this process of getting v in terms of x and y and u in terms of x and y just to make the coordinate conversion from xy to uv. So I got v equals x minus y, and I got u, well, obviously that was pretty easy. If y equals u, then u equals y, same thing. So you see I listed the coordinates right here that are given in the xy system. The order doesn't matter. And then now I'm converting to u and v. So for example, if I 0, 0, well, you put in 0, everything's 0. But let's look at the next one. xy is 4, 0. V equals x minus y. So v would be 4 minus 0, which is 4. V is the second coordinate here. And then y equals u. So y was 0, therefore u is 0. So that converts to the point 0, 4. The next one, I'll do u first this time, I guess. Y equals u for 3, 3. The y is 3, so the u is 3. The v will be 3 minus 3, which will be 0. Then for the last one, y equals u, the u is 3, so u is 3. And then v equals 7 minus 3, which will be 4. So now you can see that u has 0 and 3. It's going to go from 0 to 3, and v will go from 0 to 4. So like I said a few minutes ago, I sketched it, but the sketching is not necessary. You can actually see it from right here in the conversion, what the limits of integration are going to be without that region. It's going to go from 0 to 3 and 0 to 4. Now here's where we do the Jacobian. So we come back up here, look at the original form, x in terms of u and v. The partial of x respect to u would be 1. The partial of y respect to v would be 0, because there is no v. Minus the partial of y respect to u would be 1. And then the partial of x respect to v would be 1. So the Jacobian is actually negative 1. However, very important, the Jacobian itself is negative 1, but this number that you put in here, we're always taking the absolute value. So it's always going to be positive. Now let's look, we have to convert our integral over, our x's and y's have to be converted over to, went too far, over to u's and v's for integration purposes. And that's not difficult to do. We know that y is u, and then from over here, you can either get it one of two ways, but you could actually just subtract these two and get the same answer. But v is x minus y. So that's the first one is u, and x minus y happens to be v. And then the Jacobian is part of the dA. So it's du dv with the absolute value of the Jacobian mixed in there. And these integrals are generally pretty easy. They're not meant to be, meant to be complicated. If someone wanted to be creative, I'm sure they could make it complicated, but that is not my goal. So we're just integrating uv, du dv, 0 to 3, 0 to 4. So the antiderivative of u with respect to u would be 1/2 u squared. Put in 3, put in 0. 3 squared is going to give you a 9. So I'm going to take that 9, move it out with the 1/2, and make that 9/2. Then I go from 0 to 4, v dv. So the antiderivative of v respect to v will be 1/2 v squared. I put in 4. Now I went ahead and combine the 1/2 with the 9/2 to make 9/4, and then 4 squared is 16. So I have 9/4 times 16, which equals 36. Now, this one, I'm just showing you, you don't need to do this, but I'm just showing the integral. Actually, dx dy, if you go back and look at this original sketch, dx dy would be one integral because it's the same left and it's the same right. They don't change. But it's interesting, though, is that dy dx would have been 3 double integrals. I mean, I wouldn't trouble yourself with going through to set all this. But look at, so I'll put the first one in there. And there it is, dx dy, set it up, and I got 36. I mean, if you want to have fun and play around with that, you can. But yeah, this one, I didn't work this one out. I just let Maple do it. Yeah, so I had to piddle around with this and, you know, change. So I've got it broken out into 3 zones here. So those are the integrals that represent each of the 3 zones. Added together, look at the answer it got, 36. So that tells me that I did it correctly, or I got extremely lucky, but I didn't. I did it correctly. You see why this method has an advantage over doing it just as a regular double integral. All right, let's see what we got here. We're going to find the volume. And the function f of xy is 48xy. And then it gives you a region bounded by a square, but an angled square. That's the whole idea. If it was a square that set flat, you know, it would be, and it wouldn't have to do transformation. We are transforming it into, imagine if that square just tilted over to the right and fell flat. It wouldn't be the same coordinates, but I mean the idea visually. So this one, I just used basic. I took these points, plotted them, and then I labeled these so you could see 1, 2, 3, 4, which line. There are 4 line segments. So I just used your basic, you know, find the slope, intercept method to come up with each of these 4 equations of those lines. And I guess I could have checked these in the calculator to see if the graphs looked right, but I was pretty confident in what I did here. Then I moved the x over. Since I saw that these had the same structure, they're going to relate, and so do these. That's the idea. So the 2 going the same slope are going to be one variable, and the other 2 parallel ones will be the other variable. So if I move the x's over, and I have y minus x equals 1, y minus x equals negative 1, and it really doesn't matter which one you choose as u and v. I could have chosen either one. Wouldn't have made any difference. So now you see I have y minus x equals 1, y minus x equals negative 1. Now I know that u is going to go from negative 1 to 1. And then here, I moved the negative x's over, made them positive x. They both become y plus x, and I get 1 and 3. So we know that v will go from 1 to 3. So we're almost set, but we have to get the Jacobian. All right. So we know that u will equal y minus x, because we need y and x in terms of u and v. So we know that u equals y minus x, and v equals y plus x. So I just start looking for some, I want to eliminate either x or y, and whichever one I eliminate the first time, I have to eliminate the other the next time. So it doesn't matter. This one was real easy to get rid of the x's just by adding the x's together and canceling them. So I got 2y equals u plus v, which then gives me 1/2 u plus v equals y. Over here, I chose to multiply the top equation by -1, knowing that when I added downward, I would eliminate the y's. And that's then have it for x. So I have negative u plus v, which I just wrote as v minus u. Either way is, of course, correct. So -1 times negative x is positive x. Add them together, we get 2x. So now I get this equation. So now I know that y is 1/2 u plus v, and x is 1/2 v minus u. So I can now do the Jacobian. Okay. All right. So you might want to distribute this, be careful. We have a negative here, and the 1/2 is part of all this. So the derivative of x respect to u, if you distribute that, it's going to be negative 1/2 u. So the derivative will be negative 1/2. I wrote it out like that. And when you do a determinant, actually it's this diagonal right here, left to right, minus the other diagonal. But anyway, so it's negative 1/2. The derivative of y respect to v will be positive 1/2. So you have a negative 1/2 times a positive 1/2 gives you negative 1/4 minus the partial of y respect to u will be positive 1/2, and the partial of x respect to v would also be positive 1/2. So you have 1/2 times 1/2 is 1/4. So you have negative 1/4 minus a positive 1/4. That's not 0. That's negative 2/4, which is negative 1/2. I'm not sure. I did all this conversion over here, this business right here. But you know what? You didn't really need to do that, because I already mentioned right up here, you can pretty much establish the limits of integration from right here. It's okay that we did that, but not necessary. But there's no doubt it would go from -1 to 1 and then 1 to 3. Remember, smaller numbers always on the bottom in an integral. So yeah, I didn't necessarily need to do that. But maybe, that was kind of a check more than anything else. Once again, I was just checking to make sure that the XY coordinates converted over to the proper UV coordinates. And maybe I just did it because I wanted to show you what the rectangle looked like right there. In this case, it's a square, but once again, the sketching is not mandatory. But notice that's negative, and I put this in here. I must have put it at the ends. I probably forgot to wedge it. It doesn't matter mathematically because it's just a constant. But normally I would have put it before the du, dv. But it's the absolute value of that determinant. So that will be a positive 1/2. So what I did here is I just took 48 and multiplied it by, see, this is your x and your y, converted over to u and v. We just solve for those, remember, right up here. That's how we got those partials right there. So the original integral was 48xy. So here's x, here's y. And I just took 48 times 1/2 times 1/2 times 1/2. That gives me the 6 on the outside. -1 to 1 for u, 1 to 3 for v. And if you just FOIL out these two things in parentheses, I'll skip those steps. I figure this is calculus 3, so you should be able to do that. You're going to get v squared minus u squared. I'm not saying you have to do that in your head, but write it out, and that's what you should get. So we're going to integrate this with respect to u. So the antiderivative of v squared with respect to u would just be uv squared. The antiderivative of u squared with respect to u would be 1/3 u cubed. So we put in a 1, we put in a -1, and we still have a variable in there though. We have, because the 1 goes here, the v is still there. So we have v squared minus 1/3 minus, You put in negative 1, you'll get a negative v squared minus, you put in negative 1 here, makes that negative 1/3. It'll be minus a minus 1/3, which of course will be plus. And then that condenses down. V squared minus a minus v squared is 2v squared. And then you play negative 1/3. There's a lot of minuses there. That becomes a positive 1/3, but this negative changes it back to negative. So it's negative 1/3 minus a positive 1/3 will be negative 2/3. So it's 2v squared minus 2/3 dv, and we integrate that, put in the 6 in front, put in the 1, put in the 3, and we've got it. So the antiderivative of v squared will be 2/3 v cubed. Antiderivative of 2/3, which would be 2/3 v. So you just plug in 3, plug in 1. And just use your calculator to do that. So 3 cubed is 27. So 2/3, 27 minus 2/3 times 3. And then here you get 0, because it happens to work out to be 2/3 minus 2/3. 6 in front. This stuff in this parentheses works out to be 16. It'll be 24 minus, let's see, not 24 minus 16. It'll be 18 minus 2, which is 16. And then the 6 in front makes it 96. So I just went ahead and typed the original one back in Maple just to show you it equaled 96. And then just for fun, I set it up as a pair of double integrals added together. If we had not done the transformation, not necessary. I just did dx dy. I'm assuming that dy dx was probably about the same. Well, we can kind of look and see, but it's probably the same level of difficulty. I'm sure it's 2 regions. So I set that up and got 96. But like I said, that was just to show you that what we're doing with this process works. Now you kind of get used to these when you start working these and you start kind of getting used to the idea. Now I plotted this parallelogram, but I could kind of sort of sense here that was going to be a u and a v, and I was expecting to get one of them to be x minus y and one of them to be x plus 4y. And sure enough, that's what happened. Now I didn't solve for each of the lines. I kind of took that on faith, but then I could verify that real easily. And we could have done the same thing, I guess, for the one where I didn't actually solve. Let me go back up here. I didn't solve them, but I told you that I solved them. This right here. But this one's a little bit different, though. We didn't have any u's and v's or anything. We kind of needed to. We weren't integrating, so we kind of needed to do it this way here. We didn't have any choice. But this one, because it's associated with an integral, that's how we were able to kind of rationalize this out. And then I can plug in the x's and y's and make sure they generate a proper rectangle, a flat, normal rectangle. So I plugged in all 4 vertices of that parallelogram by using this u and v and got these 4 points, and then that means we're good. We have we have a square, but that's okay. A square is a rectangle. All squares are rectangles, but not all rectangles are squares. So that was a correct conversion, because that's always what we're looking for, either rectangle, square, something that sits like that. Then we know we're set up properly. And all right, now I'm having to do the process of converting over to where I get x and y in terms of u and v. This is where we have to do that elimination substitution process. Because we know that we're going to go from 0 to 5 and 0 to 5 for our limits of integration. That's not the issue. But we have to do this to get the Jacobian. So what I chose to eliminate. You're always doing this to where you eliminate the x and then you eliminate the y. Looks like I did a little bit differently, but all right. I don't know why I did it this way, but anyway. Maybe I was just kind of showing you another way to do it. But I'll mention what I was thinking there. This one, though, you multiply by -1, kills the x's. So you got a negative u and a v, so I wrote that as v minus u, gives me a 5y. That is y equals 1/5 v minus u. So it looks like I'm using a substitution process this time, which I haven't done before. But before I go into that, I'll explain what we could have done. We could have gone back like I did before. Then I could have multiplied top and bottom, or top equation all by 4, added together and kill the y's. That would absolutely still work. But I was just trying to illustrate how substitution would work. Since I now have the y, and I can take this equation, move the y over. If u plus y equals x, we know what y is, right? So u plus 1/5 v minus u equals x. And then I multiplied everything by 5 to get rid of the fraction. And I got 4u plus v equals 5x. And then x equals 1/5 4u plus v. So if you did not like that, that's quite all right. You could have gone with the way I did it before and just multiplied top and bottom by 4 to eliminate the y's. That might have been better anyway. Looks like that might have been a little quicker because I can already see the 4u plus v right there equals 5x right here. All right, but didn't hurt to see it a different way. So we got to do our partial derivatives to get our Jacobian. Partial of x respect to u, don't forget the 1/5, so it'll be 4/5. Partial of y respect to v will be 1/5, minus the partial of y respect to u, will be negative 1/5 when you distribute that out right here. And then partial x respect to v, right here will be 1/5 v, so it'll be 1/5. So 4 over 25 plus 1 over 25 gives me 5 over 25, which then just reduces to 1/5. And we take the absolute value of that, but of course, since it's positive, that's not critical. Absolute value is already positive, so so I took the 1/5 of the Jacobian all the way to the outside, and because our original integral is basically now the square root of u times v, and because u and v is multiplied, you can break those square roots up. Not if they were added or subtracted. People really have trouble with that. I don't know why, but it should be easy. But multiplied radicals are allowed to and divide are allowed to split up, but not add or subtract. So it is acceptable for me to break that radical up like this because they were multiplied. In fact, you need to be able to do this. And so the antiderivative, u to the 1/2, just using the power rule, is going to give you 2/3 u to the 3/2. And I just brought the 2/3 on the outside. I'll put in 5. So I left that as 5 to the 3/2. And then multiply the fractions to get 2 over 15. And then v to the 1/2 antiderivative will be 2/3 v to the 3/2. So I can multiply the 2/3 times the 2/15 and get 4 over 45. And that's going to be another 5 to the 3/2. Now, on a handwritten test, I would not expect you to have to get too cute with the answer here on this. If it's multiple choice, you could even, obviously, you could get the decimal equivalent of your answer and try to match it that way if you don't simplify it. But it does actually equal 100 over 9 precisely. So in other words, if I multiplied out my first answer in a calculator, it will be the decimal equivalent to 100 over 9. But let me explain real quick how that works. It's easy. Same base, add the exponent. So 3 over 2 plus 3 over 2 is 3. 5 to the 3rd is 125. And then actually this reduces. 125 over 45 reduces by 5 to 25 over 9. So 4 over 9 times 25 gives you 100 over 9. And here's one more to close out the video. I thought this was kind of neat because actually it's got a curved looking graph there. All right. So they're telling us what x and y are. And then you can probably bet x times y is going to be either u or v, and y will be either u or v. Doesn't matter which one, just depends on what you choose. Well, actually it does here because it told you what x and y were. But so then if y equals v, I put y in there. If and x equals u over y, I multiply. I know that u would equal x times y. And of course, if y equals v, that means v equals y. So now you can see the x times y in your integral. That's going to be your u. And then we're going to have a v out here for the y. And we need to then come up with what the new coordinates are. So I'm converting, they're not telling you the coordinates, but you can figure them out based on the equation and what they do show. So when you have 1, 1 right here, 1, 1, I put it in there, it's actually going to give you 1, 1 right here. I've got 4, 1. And 4, 1 will be 4 times 1 will be 4. And then y will be whatever v is, so it's going to be 1. Now the next one, it's real clear that the y value is 4, but it's not clear what the x value is. So that's where you have to actually use this equation. If we know for sure the y is 4 here, which is indicated by that vertical, well, it's indicated right here, put 4 in there, and you solve for x. So x would have to be 1/4. That's how you would know, not by just visualizing, just solving directly. So we have a 1/4 4 for this coordinate. Plug it in here. 1/4 times 4 would be 1. And then v equals y, so v would be 4. And then here, you can kind of see that it's 1, but you could solve for it real easy. It's the equation xy equals 4. And if y equals 4 right here, x has to be 1. So we know for sure that's 1/4. And then when you convert it, 1 times 4 is 4, and then v is y, so it's going to be 4. And we have a delightful little rectangle, square, of course, which is what we want. So we're going to be going from 0 to 4 and 0 to 4 after we get the Jacobian. Now this Jacobian is actually going to have variables in it, which is kind of interesting. So here's what we're taking the partials of. Maybe I should have copied those down there. Let me zoom out on this a little bit so we can see it. Maybe a little too small. I just want you to see the part, we can see everything with the Jacobian. So partial of x respect to u. So basically the u over v, you don't have to do a quotient rule here. It's just 1 over v, or you can think of it as uv to the negative 1. But the derivative of u is just 1, so it just leaves the v to the negative 1, or I have it as 1 over v. And then the partial of y respect to v would just be 1. We come over here. The partial of y respect to u, there's no u. That'll be 0. Now this one, you don't need to do quotient rule. If you call that here uv to the negative 1, uv negative 1, and you're taking the x respect to v, you would just do a power rule. You'd bring the negative 1 down, put it in front, change the v to negative 2, so you have negative u v to the negative 2. So it's just a product rule. And let's see how this simplifies. But the good news is, I won't explain that, but obviously the 0 wipes it out anyway. But, some other situation, you might not have a 0 there. So you ultimately end up with just 1 over v. Positive, so the absolute values are, we don't have to worry about that. We'll take the absolute value. It's already positive. All right. And then we have 1 over v times, we come back over here. Let's go back and look at our original integral. So you see that y is v, and then xy is u. I don't know why I did it this way, but I ended up at the same location, same place where it's supposed to be. You end up with sine of u right there. I just did x and y separately and multiplied them together, but I don't know why I did that, because we already know that x times y is u. Or from right there. Whatever, I didn't hurt anything, but... And then the 1 over v actually cancels the v, so it makes the integral a little less process there. So the antiderivative of sine is negative cosine of u, du dv, or dv, just dv. Put in the 4, put in the 1. Now I'm writing here that I used a property of definite integrals that to create it, if you flip the limits of integration, you create a negative. And since I had this negative here, I effectively got rid of that negative. So I moved the 1 and the 4 around, got rid of the negative. So I have cosine of 1 minus cosine of 4. Those are just in radians. Just leave it like that. Don't do anything to it. And then the antiderivative of dv would just be v. So all you're doing is subtracting 4 minus 1. So it's 3. So you have 3 cos 1 minus cos 4. Don't do anything too fancy with it. That's pretty much it. See, Maple didn't get too fancy with it either. Like obviously, we could have gotten a numerical approximation, but we didn't need to. And in Maple, I put it in there as if it would have been we hadn't have done the Jacobian transformation. So, well, all right. That concludes this video on change of variables, Jacobians.